Okay, acid-base properties of ions and salts. So some ions, like HCO3 minus, can act as bases. So these ions are conjugate bases of weak acids. So when an acid behaves as an acid and donates a proton, it becomes a conjugate base, which is then capable of accepting the hydrogen ion back. And it's just passing the hydrogen ion back and forth. So HCO3 minus can accept a hydrogen ion from water and form H2CO3 plus hydroxide. It's acting as a base. H2CO3 is a weak acid. This is the conjugate base of the weak acid. So if we have an ion like this, it can't just be by itself. You can't just have negative charges in a jar. There have to be an equal number of positive charges. You need a counter ion. So there's got to be a counter ion to form a salt. And salt is just a word chemists use to mean any ionic compound. So we could put sodium with that. Sodium hydrogen carbonate. This is an ionic compound, a salt, and not a salt like with a rifle, but a salt. I actually have a picture. It's not in these slides. Somebody spilled salt on a table and they shaped it into a rifle. A salt rifle. Yeah, I need to put that one in here. It's in my 3A notes. This is going to dissociate completely. Do we care about the sodium ion? No, it's a spectator. This is part of why we made you learn about net ionic equations, to help you understand that there's things swimming around in there that we don't need to pay attention to. So when we look at something like this, we understand that there has to be a counter ion. It could be potassium, it could be anything, any positive ion. Do we care what it is? No, we don't. But that's where it's coming from. So a solution of sodium bicarbonate will be basic because this is a salt that contains a weak base. Okay? So any anion can be thought of as the conjugate base of an acid. So A minus is the conjugate base of an acid, HA. So that's our generic way of representing an acid. It's got a hydrogen, and the rest of it is A. When it loses A, it becomes A minus. This is the conjugate base of that acid. So the example here, we've got HNO3. When it removes the hydrogen ion, you're left with nitrate ion. Nitrate ion is the conjugate base of HNO3. Anybody following me on that? Take the hydrogen off, you've got the conjugate base. You put the hydrogen back on, you've got the acid. So not every anion can act as a base, even though we could think of it that way. We could say, well, this is the conjugate base of that. But it's not necessarily going to act like a base, practically speaking. It depends on how strong the acid is. So the conjugate base of a strong acid like HNO3 is going to be pH neutral because it just ionizes completely and it's not going to go back the other way. The conjugate base of a weak acid will be a weak base. The weaker the acid, the stronger the base. So it's kind of an up-down thing. If one's stronger, the other is weaker. So if we think about the chloride ion is the conjugate base of HCl. But HCl is a strong acid, right? HCl, I'll be thorough here, since that other one's got all the stuff in it. And this is just a single arrow. Strong acid. ionizes completely. Is this chloride ion going to pick up a hydrogen ion and reform this? Is there an arrow going back? No, it's not going to do that. So the conjugate base of a strong acid, we say, is pH neutral. It's not going to act as an acid. It's not going to act as a base. Here's HF, hydrofluoric acid. This is a weak acid. So a weak acid ionizes partially, forms some hydronium ion and some fluoride ion, but this is in equilibrium. It's going both ways. So if we had fluoride ions, they could accept hydrogen ions and go back this way. If you accept a hydrogen ion, you're a base. Okay? The fluoride ion has affinity for the hydrogen ions. The chloride doesn't. I guess you could think of this as a bad parent. Not the worst kind of parent, because the worst kind of parent would just abandon their children, right? This parent is going to hand them off to the babysitter and take off. And they're just not going to come back again. I know it's not.
So does it only happen with strong acids?
That only happens with strong acids. So a weak acid, hand off the hydrogen ion, hand off the child, but then it still likes the child and eventually it's going to come back and pick it up again like a normal person would. Any questions? So here's, I don't know if you call that a table, an illustration maybe, a figure, showing acids on one side and bases on the other, and they're ordered by strength. So if we look up here, these are strong acids, HCl, H2SO4, HNO3. Well, we didn't list H3O+ as a strong acid. But does it make sense that we could consider that to be a strong acid? It's not going to, well, anyway, it's considered a strong acid. These are the conjugate bases. So these are strong, these are weak, okay? I'm sorry, these are so weak that they're neutral. They're powerless. As we go down here, we're getting weaker and weaker acids. Here are the conjugate bases. As the acid gets weaker, the conjugate base gets stronger. Does that make sense? A weak acid only ionizes a little bit, so you've got a little bit of that conjugate base. You only have a little bit because it really likes the hydrogen, and it's going to take it back as soon as it can. Down here, we're going to learn that the conjugate acid of a strong base is also neutral. So HS and minus and OH minus are just can't really be considered acids at all. Okay. Classify each anion as a weak base or pH neutral. What we're looking at here is what is the acid that this is the conjugate base of. So to take a base and make it into the conjugate acid, to make a conjugate acid-base pair, you're just going to deal with the hydrogen ion, right? So if we put a hydrogen ion on this, what do we get? CHO2H. You could write that a couple of different ways. So this accepted a hydrogen ion, right? It acted as a base. We want to look at the acid that it forms and ask ourselves, is that a strong acid or a weak acid? Which is it? Weak. Like, I don't recognize that acid. That's okay. It's not one of the six, right? So this is a weak acid. My pen, my Apple Pencil's complaining that I've dropped it too many times. It's right. So if this is a weak acid over here, is this going to act as a weak base? Yes. So this is a weak base. That make sense? Good. HClO4. What's the conjugate acid? HClO4. What kind of an acid is that? Strong acid. That's a strong acid, means it ionizes completely. It's not going to come back the other way. So, is this a weak base or pH neutral? It's going to be pH neutral. It's just going to be out there. It's not going to act as an acid or a base. Any questions? Okay, let's see thumbs. Good, confused, lost. Okay, I think I got enough slightly not up. So let's see here. So this first one was a weak acid. And the second one is a strong acid. This is what I'm trying to figure out if it's a base or not. I'm going to look at, well, what kind of an acid did it come from? So I'm going to put a hydrogen ion on it and look at it. This is a weak acid. So it ionizes partially. This goes both directions. So if I had a solution here and I had none of this and I put some of this in there, you always have at least a little bit of hydrogen. Would this pick up hydrogens and make some of that? Yeah, it would. That's acting as a base. Here we have a strong acid, ionizes completely. If I put perchlorate ions in a solution, is it going to pick up a hydrogen and become HClO4? No. This arrow only goes in one direction. Does that help at all, sideways people? Any questions? Yeah.
So in the first example, a weak base corresponds to a weak acid. In the second example, why wouldn't a strong base correspond to a strong acid?
That's a good question. If a weak base corresponds to a weak acid, why doesn't a strong acid correspond to a strong base? A strong acid does not correspond with a strong base because the idea that it's strong means it only goes one way, it only acts as one thing. So I guess you could say that the strong acids and strong bases have very strong, maybe sense of self. They know who they are. It's like, no, I don't want that hydrogen, or yes, I do. And they're not going to waffle back and forth. Whereas you could think of a weak acid and a weak base as they're kind of waffling. I could go either way. Does that help? Okay. Any other questions? Okay, so we can figure out the pH of a solution that has an anion that acts as a weak base. We need to know the Kb for that anion. Okay, so this is telling us derive the relationship between Ka and Kb. Again, I'm going to show you this. I don't expect you to do this on an exam or anywhere else. And now I'm looking at it and I'm like, what was I telling myself to do here? I don't have any notes on my slides. It makes life more interesting for me. Well, here we have a weak acid, right? Ionizing. So we could write the equilibrium expression for that. H3O plus, products over reactants. Water's a liquid, doesn't show up. Here we have an anion acting as a weak base. It's going to accept a hydrogen from the water to form hydroxide and HA. This is the equilibrium expression for a weak base. So we got hydroxide ion and HA, and down here we've got A minus. Everybody okay with that? This is Ka because we're starting with an acid. This is Kb because we're starting with a base. How do we know that's a base? Well, we look over here, it made hydroxide ion. This is an acid, it made hydronium ion, or hydrogen ion. There's another equilibrium constant called Kw, and that's the one for water, right? We learned about that one. That's H3O plus times OH minus. I'm going to kind of do this from the back end. What we're going to end up with is Kw is equal to Ka times Kb. So that means that this would be equal to this guy. Times this guy. Okay? I'm kind of cheating because I know what the final answer was. I think this might just make more sense. Kw equals Ka times Kb. So this is what Kw means. This is Ka. This is Kb. Well, if we look at these, there's an A minus on the top and bottom in both of these. Those are going to cancel out. And the HAs are going to cancel out. Hydronium plus hydroxide is equal to hydronium times hydroxide equals hydronium times hydroxide. So this is the relationship that we're going to use. There's other ways you could demonstrate that, but that's what came into my head just now. Any questions? Determine the pH of a 0.250 molar NaC2H3O2 solution. Ka equals 1.8 times 10 to the minus 5. Okay, these are practice questions. They have a title up here, which kind of gives us a clue. Determining the pH of a solution containing an anion acting as a base. That's our clue. We have an anion acting as a base. Let's look at this thing that we have here. That's an ionic compound, right? It's a metal and something else. So that NaC2H3O2, that's going to separate into sodium ions and this other thing, which you may or may not recognize, acetate. So again, this requires some knowledge from Chem 1A. In Chem 1A, an ionic compound always had one cation, one kind of cation. It could be calcium 2 or something, but you wouldn't have calcium and phosphorus or something. One kind of anion, and everything else was the one kind of cation, and everything else is the anion. So we take that thing and we split it up, right? So this is the anion that we're looking at. We don't care about the sodium. We're going to pretend it isn't there. It doesn't matter. So I'm going to take this and see how this can act as a base. Oops, forgot the minus. So if it acts as a base, it picks up a hydrogen ion, right? The babysitter picks up the child. So it's going to become HC2H3O2. And then what's left is hydroxide ion. Yes?
Can you explain why it's transferred out from that top part with the NA?
Why we took this apart?
Yeah.
Yes, I can. So here, they give us this formula, and sometimes they're going to look pretty weird. It's, yeah, that's nacho, basically. The first element is a metal, right? And the rest of them are nonmetals. In Chem 1A, at least I taught my students, you recognize that as an ionic compound, right? You got a metal, nonmetals. You've got two ions, one cation, one anion. So what we want to do here is we want to separate those ions. So Na, Na plus, because of its position on the periodic table, we know it's a +1. When we take that off, everything that's left is together, and that's going to have a minus. Does that make sense? So they're probably going to give you the name of the compound, not just the anion. And you have to recognize what's the anion, okay? So whether you write this out or do it in your head, that's what we're looking at. Sodium is just a bystander. It doesn't do anything with anybody. Sodium ion just doesn't react. It just doesn't. So it's just going to hang out. So this is the part that we're interested in. So we see that it doesn't have an H on the front, so it can't be an acid, right? What happens if we try to make it act as a base? So a base, you put in water, and it's going to accept the hydrogen ion and produce hydroxide ion. Okay? So I identified what the anion was up here, and then I said, okay, this is my base now, and when it acts as a base, it picks up a hydrogen ion. So here it's going to get a hydrogen ion from the water and make this. This was our base. This is our conjugate acid. Okay. What kind of an acid is this? Strong or weak? Not strong. Right? It's not one of the six. This is a weak acid. It's acetic acid. You may or may not recognize it. That's okay. And here they're giving us Ka. That's the Ka for the acid. They're not going to give you Kb for the anion because this is recognized as an acid. So, if you go looking in the tables of the book, you're not going to find it. Put an H on it, and you'll find the Ka for it. So we need an ice table. I'm tired of drawing lines. So what's our initial concentration of C2H3O2? 0.250 is what was given. And we don't care about the water. Initial concentration of the conjugate acid here would be 0, right? Initial concentration of hydroxide ion, approximately 0. Because all we had was this guy. So then we look at the changes. We've got to have plus X over here, minus X over there. So let's write equilibrium constant expression for this. This is a base, so what we're writing is Kb, not Ka. Kb will be HC2H3O2 times OH minus.
Wait, why is it KB again?
It's Kb because the base is on the left. A Kb expression is gonna have hydroxide ion concentration in it. A Ka expression is gonna have hydrogen ion concentration. And you can't just turn it around. That would be really great, but you can't just do that. So here I have this acting as a base. I'm gonna write the equilibrium constant expression for that. And it's these guys. So I know that if I know what Kb is, I can plug this stuff in and find out what X is. But they didn't give me Kb. They're almost never gonna do it. You have to calculate it from the Ka. So Kw equals Ka times Kb. So Ka equals Kw over, that's not what I wanted. No, that is what no. I don't know what I'm doing. Don't listen to me. Yeah, who else would you listen to? I guess I know more about this than anybody in the room, so you have to listen to me. But I also am human. Okay, so we can calculate the Kb then. Kw, 1 times 10 to the minus 14, divide by the Ka that they gave us. I'm getting 5.555 forever times 10 to the minus 10. The Ka had 2 sig figs, my Kb will have 2 sig figs. I'm just keeping 2 extras so I don't have to worry about rounding problems. And I don't have nearly enough space left. It's pretty typical. So I'm gonna squeeze it in here. 5.556 times 10 to the minus 10 is gonna equal the HCH3O2, which is X, times the OH minus, which is also X, divided by this guy over here. Could we do X as small? We could. The book's going to do it. I don't want to. So 5.556 EE minus 10. And if you used your solver before, it's already set up in this form. You just have to change the numbers. So what does X represent? It represents the change. It also represents the hydroxide ion concentration at equilibrium. What are we trying to find? pH. So I'm going to find the POH of this and subtract it from 14. So the POH, negative log of that, so 4.9287. pH is 14 minus that. So here we're determining the pH of a solution having something that acts as a base. Is this a reasonable pH? It's above 7. right? Which tells us this is a basic solution. So that makes sense. If we were trying to say that the answer was 4.92, 4.93, wait a minute, that's an acidic solution. This has a base in it, it should be basic. So this is the same idea as the weak acids, but it has a couple of complications in it, right? So you've got this guy, and so you're going to write out this equation. You make the ice table. That's all good. You set up the equilibrium constant expression, but they didn't give you Kb. So you have to calculate Kb. And then you find out what X is, but X is a hydroxide. It's not the hydrogen. So you have to convert it before you can get the pH. So there's two extra things you have to do with the weak bases. Any questions? Which anion acts as a weak base?
C,
Yeah, it's C. What are we thinking about here?
whether it's from a weak acid.
Yeah, we're looking at, is this the anion from a weak acid or a strong acid? So this would be coming from HCl. This is coming from HBr. This is coming from HF. This one's strong. This one's strong. Not strong. Yes?
So you can tell by knowing if it's part of one of the 6 strong acids?
Yes. Yep. So we're looking at an anion, and that we can always stick a hydrogen on it, or more than one hydrogen on it, and write it as an acid. Then we ask ourselves, well, is that a strong acid or a weak acid? If it's a strong acid, if it ionizes completely into hydrogen and chloride ion, and it's not going to go back, so the chloride ion doesn't get a chance to act as a base. But HF is a weak acid. It only ionizes partially, and so there is that backwards reaction where fluoride acts as a base. Any questions? But the fun doesn't end there. Anions can act as weak bases. Cations can act as weak acids. Oh, joy. I told you about the simpler one first. There's 3 categories of cations. So we can think about cations that are counterions of strong bases. So examples are calcium, sodium, potassium. Because the strong bases are metal hydroxides, right? So strong bases dissociate completely, and so their counterions don't ionize water. So NaOH dissociates completely. So this is not going to go backwards or do anything silly like that, okay? If you've got a strong base, the counter ion is pH neutral, doesn't act as an acid or a base. What about cations that are conjugate acids of weak bases? A cation that is the conjugate acid of a weak base is a weak acid. That's, yeah, just so many words jumbled together. So a cation can be formed from a non-ionic weak base by adding a proton to its formula. So if we add hydrogen ion to our weak base, B for base, that makes this able to act as an acid. It has a hydrogen ion, it can donate to water, forming a hydronium ion, and you get the original base back. So weak acids and weak bases, they just pass the hydrogen ion back and forth. Whoever has the hydrogen ion is the acid, Whoever doesn't is the base, because they're the babysitter, they could take the hydrogen ion for the adult acid at any time. Are you okay with that? So, the pH of a solution that has the conjugate acid of a weak base can be calculated using Ka. That would be a process much like what we just did. Here, they would tell us what Kb is, and we'd have to figure out what Ka is, but we'd make a nice table and do all of that. And then there's this other group. The bases, their ions, they were either of a strong acid or a weak acid, so they were strong or not, weak base, you know what I mean. Anyway, so here we had the conjugate of a strong base, pH neutral. Conjugate of a weak base can act as an acid, so it's a weak acid. And then there's this extra group for the cations. Small, highly charged metals. These are things like aluminum 3+ and iron 3+. These are small, they're only in the third row of the periodic table. I'm sorry, the fourth row of the periodic table. And they have a high charge. So what these guys do, and I don't really expect you to completely understand this, just believe me, okay? That ion can become hydrated. So here we have the ion, and it's just got a bunch of water molecules hooking up with it. How does it even do that? Well, each of those water molecules has a lone pair. This small, highly charged ion has an empty electron shell. And so the waters are like, oh, you're naked. I'm gonna share my electrons with you. And they'll do that. So then this hydrated ion can act as a Bronsted-Lowry acid. Bronsted-Lowry acid donates a proton to something else. So one of these hydrogens on these water molecules could be donated to a loose water molecule to make hydronium ion. I don't expect you to be able to explain that to me or repeat it back to me. What I expect you to know is that Al3+ and Fe3+ act as weak acids. Just remember it. Okay, here's the cations. Classify each cation as a weak acid or pH neutral. Again, let's look at the base that this would correspond to, right? So lithium hydroxide, what base does that come from? Did I say lithium hydroxide? I did. Yeah, lithium comes from lithium hydroxide. I meant to say, what base does lithium ion come from? It comes from lithium hydroxide. Is that a strong base? Yes. Yeah, it is. So this is pH neutral. It's not going to do anything. Okay? This thing. I don't know who that is. There's a nitrogen in here, and there's hydrogens on the nitrogen, and there's a plus. So this is a lot like NH4+. Let's see what happens when we take a hydrogen off. So we're trying to figure out, is this going to act as an acid? Well, it has a hydrogen ion it can donate here. When it donates that, it's going to make this. You should recognize this as a base because it's got a nitrogen with carbons and hydrogens. That nitrogen has a lone pair. So you see any kind of mess like that with a nitrogen in it, that's a weak base, because I told you. So if this is a weak base, can this act as a weak acid?
Yes.
Yes, it can. So that's a weak acid. And then what about this guy? Fe3 plus. Yes, this is one you just need to remember. Fe3 plus and Al3 plus act as weak acids. Is that going to be a huge part of the class? No, it's not. But give it your best shot. Any questions? Okay, now we're going to make it more fun. We're going to put anions and cations together and see what happens. So, classifying salt solutions. Salts have cations and anions. The cation has a possibility of acting as a base. The anion has a possibility of acting as an acid. So there's different combinations. The first one is a salt where neither the cation nor the anion acts as an acid or a base. So they're not going to do anything, so then this is going to make a pH neutral solution. This will happen when the cation is the counter ion of a strong base, like sodium ion, potassium ion from sodium hydroxide, potassium hydroxide. And the anion is the conjugate base of a strong acid. So examples of salts that are pH neutral, NaCl. So to recognize those, we need to look at the two ions in there, right? We've got Na plus, we've got Cl minus. What base does this come from? NaOH. That's a strong base. What acid does this come from? HCl. Strong acid. Neither of these is going to do anything. Calcium nitrate, the calcium would come from calcium hydroxide, also a strong base. The nitrate comes from nitric acid, strong acid. It's not going to do anything. Okay? Salts in which the cation doesn't act as an acid, but the anion acts as a base. So here, the cation would be the counterion of a strong base, and the anion is the conjugate base of a weak acid. The words just, I don't find them all that helpful. Let's look at the examples. Let's do this one. KNO2. So what are the two ions there? We've got potassium ion and NO2 minus. Nitrite, but you don't have to know that. What kind of a base does this come from? Potassium hydroxide, a strong base. Is this going to do anything to the pH of this solution? No, that's not going to matter. What acid does this come from? HNO2. Strong or weak? Weak. Weak acid, that means this can act as a weak base. Questions? This is when it takes a while. This mess here. We got calcium ions. What base does that come from? Calcium hydroxide. That's a strong base. It's not going to do anything. The other thing we have there is C2H3O2 with a -1 charge. What acid does that come from? Acetic acid, or H2CH3O2. Take this guy, slap a hydrogen ion on it. What do you get? Well, there's the acid. Weak or strong? Weak. This is a weak acid, so this is a weak base. I guess you could think of it as there's a limited amount of strength that would be shared between the cation and the anion, or between the acid and the base. This is a weak acid. It can't hog all of the strength, and so the conjugate is also weak. This is hogging all the strength, so the conjugate has no strength. It does not act as an acid or a base. I don't know if that helps. Here, this guy is related to a strong base. It's hogging all the strength. The calcium can't do anything. But if the conjugate is a weak something, then what you're looking at is also a weak something. Okay, salts in which the anion acts as an acid and the anion does not act as a base. So here, the cation could be the conjugate acid of a weak base, or it could be one of those small, highly charged metal ions. What are the two we need to remember? Fe3 plus and Al3 plus. This is like Iron Man, and that's Al. Al. Iron Man and Al. Just a guy named Al. Well, we see these guys a lot because they're the small, highly charged atoms, and so I gave them names. Yeah, so Fe is iron. So this is Iron Man, because I like Iron Man. And this is Al. Al would also be a guy, I guess. I don't know. That's just... So, in case you haven't noticed, I have a very dry sense of humor. And a lot of the things I say, I'm not really expecting anyone to laugh. I say them just to amuse myself. Okay? So that's one of those things. Thank you for asking. You're welcome to ask anytime. That was just something that I found amusing. Okay. So the cation is a conjugate acid of a weak base. It's the conjugate of a weak base. Is it then a weak acid? Yes, it is. The anion is the conjugate base of a strong acid. The strong acid hogs all the strength, so the conjugate base cannot be a base. So let's look at these guys. So FeCl3. This, if we try to think of a conjugate, we're like, iron hydroxide, I don't know about that one. Oh, this is one of those things that we have to remember. This is going to act as an acid. This guy, what's that related to? Hydrochloric acid. Strong acid. So weak that it's nothing. So this is going to be pH neutral. That's going to be acidic. The solution will be acidic. Let's look at this guy too. Now, this is the one place where you don't just take off the first element. The first element is nitrogen. Is that a metal? No. So, ionic compounds like this guy, it was a metal and then something else. So this is the one weird one. Look at the next one, H4, and hopefully that looks a little familiar. That's ammonium ion as a cation all by itself. And then the other part is the Br minus. So we have to be able to separate it into the ions so that we can look at them individually. Is this the conjugate acid of a weak base? Yeah. How do we recognize that? Well, it's got a plus on it. So let's think about, what if we take an H plus off of it? What do we? Weak base. This is a weak base, this is a weak acid. Bromide. That's related to HBr, a strong acid. The strong acid has all the strength, it doesn't let the anion do anything. So Br minus is pH neutral. So this acts as a weak acid. Any questions? And then the fourth group is a mess. Here we've got the cation acting as an acid and the anion acting as a base. So they're competing against each other, right? So is it going to be acidic or basic? It depends on who is stronger. So you have to look at the Ka of the acid and the Kb of the base. And whichever one is bigger is going to dominate. So just looking at these guys, we couldn't say it's going to be acidic or basic. We could identify, oh, there's Fe3+, right? That's that. So we have to understand conjugate acid-base pair. So F-, what would its conjugate be? Can we take an H+ off of it? No. Could we put an H+ on it? Yeah. So we could make HF. So there's our pair. What we've got here is the F-. This is the pair. This is the acid, that's the base. This is a weak acid, so that's a weak base. Yeah. Here we've got that NH4 again. What's the conjugate of that? NH3. So this has hydrogens and it has a plus charge. We could take a hydrogen ion off of it and get NH3. And that's a conjugate acid-base pair. This is a weak base, therefore this acts as a weak acid. What if we were a little confused, like, we're taking an exam and our stress is through the roof, and we didn't go this way. We're like, oh, well, I'm going to put an H+ on that. NH5 2+. What? Nah, that's ridiculous. Go the other way. Put an H+ on it. If that looks ridiculous, try taking an H+ off of it, and you should come up with something that looks like a conjugate acid-base pair. If one is strong, the other is powerless. If one is weak, the other is weak. The weaker one is, the stronger the other is, because they've got like this limited amount of strength, right? And they can share it between them, or one can hog all of it. That's a new analogy I just made up today. I don't know if it's good or not, but there it is. Any questions? This is a summary of that. Table 17.9 from the book. Not sure if it's actually helpful or not, but there it is. What do we need to be able to do? And this is not a critical part of Chem 1B. Ice tables are, equilibrium constants, those sorts of things. This is not a critical thing, but there will be at least one exam question on it, okay? Determine if the solution formed by each salt is acidic, basic, or neutral. So now we probably have all the combinations in here, right? So what we want to do is we want to look at the salt that we're given. It's an ionic compound, and we're going to separate it into the two ions. Well, here, sodium is a metal. That's the first ion. And the rest of it together is the anion. Don't try to make 3 ions out of it, just 2. So here we have sodium ion and we have hydrogen carbonate ion. And we look at each of them individually to see if they could act as an acid or a base. Na+. That's from NaOH, a strong base. What if you were stressed on an exam and you're like, well, I was supposed to add a hydrogen or take a hydrogen away? Well, if you add a hydrogen to that, that's ridiculous, right? So that's not going to happen. I can't take a hydrogen away from it. It doesn't have a hydrogen. So what then? Well, stick it with OH and see what it looks like. Oh, that looks like a strong base. Is that going to affect the pH of the solution? No, it's not. No effect from that one. Okay, this guy. What's his conjugate? H2CO3. Weak acid, strong acid? Weak acid. Therefore, this acts as a weak base. So this solution is going to be basic. Isn't that fun? Yeah, so fun. We should make a party game out of it, right? No one would learn the rules. Okay, let's look at this guy. What? Carbon is a nonmetal. CH3, that's not like NH4 plus. What is going on here? Look, there's a nitrogen in there. Let's look all the way at the end. What do we see? Cl. Oh, that looks like an anion, right? So these guys are a bit tricky. So we're going to pull these apart. I'm going to pull off the Cl at the end. We know that that's Cl minus, right? And that means that the rest of this has a positive charge. What's the conjugate for this one? Take off a hydrogen. Okay, that didn't help. Well, it's supposed to help. Do you see that nitrogen in there?
Yeah.
Nitrogen with hydrogens and carbons, weak base. If this is a weak base, that's a weak acid, right? Chloride, what's that a conjugate of? Hydrochloric acid. Strong acid. So this does not do anything. So the conjugate here is a weak base, and that makes this a weak acid, and so this is going to be acidic. KNO3. Well, at least we can recognize some ions here, right? K plus. Oh, I should do a different color, I guess. K plus and NO3 minus. K plus, well, I can't take a hydrogen off of it. If I put a hydrogen on, that looks just weird. Maybe this is from a strong base, like KOH. Oh yeah, that's familiar. Okay, KOH, strong base, right? So then this doesn't do anything. This is strong, this is powerless. Doesn't do anything. Nitrate. That's related to HNO3, a strong acid. So the nitrate is powerless. So this solution will be neutral. Because neither can act as an acid or a base. Any questions? Let's look at this guy. First element's a metal. There's our ion. And then we've got NO3. NO3 has a -1 charge. There's 3 of those guys, so this must be Fe3+. That's Iron Man. This is going to act as an acid because Al3+ and Fe3+ act as acids. What about the nitrate? Well, it hasn't changed since the previous example, right? It is still from a strong acid, and so it is powerless. So this will be acidic. Notice they didn't give us one where they were fighting against each other. You might find those in the homework. I won't put those on an exam. I don't think they're very nice. One more slide. Oops, there's all the answers. Which of these forms an acidic solution? If it forms an acidic solution, it has to have a weak acid in it, right? So let's look at these guys. Anions can act as bases. Cations can act as acids. How do we remember that? Maybe because we usually say acid-base, the acid comes first, the cation comes first. These guys could be acids, these guys could be bases. So we don't need to look at the anions at all here. We're going to look at the cations. Well, Na and K, sodium hydroxide, potassium hydroxide, those aren't going to do anything, right? NH4+, that's related to NH3. That's a weak base, making this a weak acid. So this is the one that's going to be acidic. Any questions? Yeah.
So wouldn't it be that Cl minus and HBr make HBr and HCl?
Say that again?
So it wouldn't be the case that the Br minus and the Cl minus would make HCl and HBr?
So they would. This would be from HBr, strong acid, so this isn't going to act as a base. This is also from a strong acid, not going to act as a base.
So we need to look for it to have act as a base for it to be an acid?
Because of how they're asking the question, they're asking which one forms an acidic solution. So it's the cation that could possibly be acidic, and that's why I just looked at the cations. And this was the only one that can act as an acid. If we said, well, which one of these forms a basic solution? Well, then we want to look at the anions. And then we'd be looking at these, and they're conjugates of strong acids, so they don't act as bases. Does this act as a base? Yeah, it does. So this would make a basic solution. But the original question was, which makes an acidic solution? And this couldn't possibly make an acidic solution, so then we don't worry about it. That make sense?
Yes.
Yeah. You could go through them like we did in the previous problem and identify acidic, basic, or neutral, and then, oh, I want the acidic one, and pick that one out. Questions?